Hello, class. All right, review day. So I got some outlines, I got some questions. I hope you have some questions, have some demos to help review some of the end stuff. And away we go, because test is on Friday. When do you get your superhero papers back? When I finish grading them all, which haven't yet. I intend to give them back to you before the semester's over, definitely. So, still working on them. All right, I have in front of me homework 7 and homework 8 and exam 4. So I can review and look and see and make sure I'm telling you things I want to tell you, and when you got questions. No, I don't want to start with that. I want to wait a moment. I want to ask first, any dying questions? Well, yeah. If you make a coil of wire at home and you wrap it around rubber, oh, like if I took this, because it's covered with insulation or rubber, if I just made a coil like this, does that work? What do you guys think? So you said that emphatically. Why? Yeah, he said, you remember the one with the light bulb attached to the coil? It was the secondary of a transformer. It's still lit. Yeah, you're correct. It would still work. Actually, an insulation on your wire is beneficial, critical. If you took a conductive wire, bare steel wire, and made a bunch of turns, they're all touching each other to the side. And so to the charges, it would act like one fat loop. So by having the insulation on it, a lot of times the wire, you look at it and it still looks like it's wire, but it has some like enamel on it, which is an insulator. Like that ring shooter I had, the thing I put the light bulb on top of. It looked like all the wire was touching each other, but it was insulated with enamel so that each loop couldn't touch adjacent loops. Otherwise, it just shortened it across, and it just acts as one loop. So insulation would definitely work. And the more turns you have, the stronger the magnetic field. The more current you send through it, the stronger the magnetic field, because there'd be a greater flow rate of charges. They're moving faster on average. What I thought your question was initially, if you wrap the wire around a rubber rod in the middle, will that affect it any? Who said no? Tell us why. Rubber's an insulator. That means charges can't flow on it. Rubber doesn't get magnetized, right? It would still be exposed to the coil's magnetic field, but it wouldn't get magnetized like iron. And if iron gets magnetized, then it has its a temporary magnet. It becomes a magnet and adds to, and that's what increases it. So yeah, rubber wouldn't help. I think that's the only time I blew a fuse as a kid. I was out in the garage, wrapping a bunch of wire around some big nail, and I didn't do enough turns. So I plugged it right into the outlet, of course, and blew a fuse or a breaker, I don't remember. And my mom comes running out, "What the heck are you doing?" Well, it should work, Mom. I just had to add more turns. Why did it blow a fuse? Yeah, a fuse blows when too much current goes through it. So my circuit, my coil, that's all I had, a piece of wire plugged directly in that just turned a few times. Why did that draw too much current? Not enough resistance. By Ohm's law, in the relationship that means a lot of current flows for the same voltage, there must have been not enough resistance. And it wasn't. It was almost like a short circuit, like taking a fork and sticking it in and just shorting across from one to the other. I didn't have enough turns. It didn't have enough resistance. So I added a whole lot more and I had a lot more wire to get through. That increased the resistance, didn't draw as much current, didn't blow the fuse, and it was an electromagnet. It worked. Okay. Other questions? Number 12 on homework 8. So I got to remember what that one is. Compared to the primary voltage, the secondary voltage may be larger, smaller, the same, or all of the above. Who put larger? Who put smaller? Who put larger or smaller? Who put the same? Who put all three? Okay, we got either larger or smaller or all three. Okay, voltage gets stepped up and becomes larger when? What has to be true in your transformer? True. If this is, well, you can't really see. If the primary has less turns than the secondary, if there's more turns in the secondary, the voltage will get stepped up. And vice versa, step down. So larger and smaller for sure. How could it be the same, or could it? If both sides have the same number of turns, then the voltage stays the same. So it can be all three. It could get stepped up, stepped down, or stay the same. Yes?
So the voltage will be stepped down if you have more turns on the other one? You have more resistance. Voltage has to push harder?
Number of turns of coils on the primary, one being the primary, voltage on the primary. Number of turns on the secondary, voltage on the secondary. With me? If this increases, so does this. It's a direct ratio of the voltage. So if you step up the turns, then the voltage steps up by the same ratio, and vice versa. So if these are the same number, then these are the same number. Okay, who's asking yourself but not raising your hand, what the heck would you ever want to do that for? You are? Give us more. Tell me what you're thinking. Yeah. How does that protect? Good. Yeah, he says, remember, these are not electrically connected directly. This wire doesn't touch this wire. Charge can't flow from here to here. So if you have a surge in electricity or a big spike or something, that'll create a big magnetic field over here. Could spike the current. But that surge makes only a brief change. It can induce something over here, but it doesn't change the voltage. Doesn't make. You can protect your circuit. Sometimes they're called one-to-one. Sometimes they're called isolation transformers. That just means they're the same turns. Perfect. No, that's an optical. Well, it could have worked. We do an EKG, electrocardiogram, where we measure the voltage across the heart, because there's cells and ions moving in and out of cells. You separate charges, positive and negative. You get an electric field. There's a voltage. That makes charges flow. Your heart actually produces a little current. And you can figure out which direction that's going. Your big ventricle contracts and pushes blood this way, but the signal changes direction. Bottom line is, an EKG or an ECG, they put electrodes on you, and it's like figuring out what's the potential difference, the difference in voltage between this point and this point. And you can get a signal. Why did I say all this? Oh, because the probes they do to use that, you want to be isolated from the power supply. You're reading currents. Well, what if while you're plugged into the system, lightning strikes? You don't want it to go through that and electrocute your person, because they're electrically connected well to your system. So an isolation transformer would be very helpful there. A lot of times they do it through optical light too. They'll convert the signal to an optical signal and transmit it that way and then convert it back. So there's no actual electrical connection. But anyway.
I was just curious, last class period, you
Okay, close enough. So I had power over here. It was alternating AC current. Went through the first bulb, then a transformer, then the second bulb, and another transformer. Okay. This one was dimmer. Is the voltage getting stepped down or up? Down, and it was a factor of 2. I had 440 turns, 220 turns. So it's by a factor of 2, so the voltage gets stepped down by a factor of 2. What happens to the current? Stepped up by a factor of 2, because power is current times voltage. And this product ideally stays the same here, 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 and here. Transformers don't produce power. They conserve it. They can step up or step up, step down, or keep the same voltage. So if the voltage went down by 2, the current went up by 2, and then the reverse, back to where we started. Why was this one dimmer? Who wants to take a stab? I think that's the crux of your question, right?
Because the current was higher, the voltage was lower, and there was less potential energy flowing through the light.
Less energy per charge?
Yeah.
I'll go with that. It's because I had the same question when I was a student. And I won't lie, I don't have a great answer. But the power should be the same. And ideally it is. So that means you're getting the same energy. So why is it dimmer?
Well, I thought that current, the more current you have, that's like what heats up the filament. Because there's more charges being moved through, heats up the filament, or filament gets the particles keep moving, or filament gets rapid. So I just kind of work here.
Actually, when things, as things heat up, their resistance changes. I showed you more when things got cold, their resistance decreased generally. So when things get hotter, including light bulb filaments, generally their resistance increases, which can affect the current that way too. I'm not coming up with a clear way in my head to explain that. But I can tell you for sure, and one of the dominating factors, is that these are not ideal. And even though everything I just told you should work, if this is 120 volts, this should be 60 volts. It wasn't. It was like 48 volts. How come we're not getting it all? Because somehow the energy of this magnetic field being, the change translating over it into this field, it wasn't complete. Some of it was lost, converted to heat, and escaped our system. And so you don't have as much total energy here as you do here in real life. And that same thing happens when you step back up. This one should go back to 120 volts. It doesn't. It might get back to 90 volts because you lose some in each transformer. And so, especially a basic transformers like I've been showing you, those are not very efficient. And there's quite a significant drop. Yes?
I have a question. So yesterday when you were talking about this, I had a different formula in mind because P equals IV. That wasn't the one it wasn't on the board, so I was thinking of current is voltage over resistance. And according to that one, seems that if current or either current or voltage were stepped down by half, then so would the other one. So how does that work there?
Yeah, here it's a direct relationship. If you cut one in half, then the other gets affected by
That's
two.
what I was thinking. So why is it not the same?
Because more than one thing changes, unfortunately. It doesn't keep it as straightforward. Because as we talked about, both of these are changing, and so does that, because of the temperature. As more flows through it, it heats up, changes its resistance, and they don't all go the same. It's not as straightforward as you just mentioned. You can rearrange this guy too and plug it into here, and you get different versions. Let's see. Like if that's current and I plug that in for I over here, you get V squared over R. Or if you do it a different way, plug that in for V, you get I squared R. 3 ways to look at power if you only are seeing 2 of them. I don't want to deal with voltage, or I don't want to deal with resistance, or I don't want to deal with... Unfortunately, all three are being affected in that system because the light bulb's temperature changes and affects the resistance as well. So it's not a controlled environment because all three are adjusting.
So, how much voltage controls upright voltage?
Yeah, I used to try to do that as a student. I tried. Oh, so it's the current that determines the brightness. Oh no, it's the voltage that determines. No, it's the power, because that's the energy that the light bulb's trying to use. And one way or another, this guy is not getting as much power as we started with in real life. And so, yeah, he's significantly dimmer. It depends on the device you're trying to power. You can kind of play those games. Oh, it's the current that matters. Oh, no, it's the voltage that matters. And you can kind of get away with it. But if you change your device, it changes. And I don't want to make any general assumptions for you to throw you off. Other questions? Oh, yeah. Yes, that is a factor. That is a factor. This guy is in a circuit with him and him. He's electrically connected to those coils. They have resistance and something else called inductance. And that affects the power that he gets also. And that is a factor. I chose not to get into the electronics of it, but since you brought it up, that's two of the demos. It was at the very end of chapter 5. And I at least had two cool demos to show you the effect, because you can understand the effect anyway. This is 9 volts. This is a huge inductor. Basically, it's a whole lot of turns of wire, a lot of coils. So when you send current through it, there's a significant magnetic field. I connected a little neon lamp to the top. It won't light unless there's a difference of about 70 to 90 volts from one side to the other. This is only 9 volts. So if I touch it, 9 volts is going through the coil and the bulb, but it's not enough to light the bulb. But when I remove it, it can flash. So I connect 9 volts, current's flowing, then I disconnect it. And every time I disconnect it, I can get more than 70 volts out. And the process there is current's flowing, lots of turns, so a huge magnetic field. What happens to that magnetic field as soon as I stop current from flowing? Does the magnetic field persist? No, because there's no more charges moving to create it. So it collapses and quickly. Remember, change is the key. So a huge change in magnetic field. It's set up and it's running when it's touching. It's happy. And then I go, whoop, no more. And it collapses like that. So a huge decrease in magnetic field, which that change in magnetic field induces what? A voltage. That's electromagnetic induction. A voltage in what? The same coil. This is self-induction, which causes a current to flow. And it's enough to, it's over 70 volts induction there, even just from a 9-volt battery. It doesn't. It's because I can't hold still. When I first touch it, it doesn't. Oh, the change is not abrupt enough. The current starts flowing. The current doesn't start flowing as quickly. It's coming and it kind of ramps up. When it starts flowing, like that. But now it's usually when I do it, it stops, and that change is a lot more abrupt. It just as soon as I stop, it has to collapse, but it takes longer because of all that resistance of the coil. So there's a whole lot of wire in there to ramp up. So it's not symmetric, as you're seeing. Here's a more zesty version. This is a huge electromagnet. there's a lot of turns of wire in here. More than that. So I'm going to play the same game. Let's turn it on. Close the switch. I'll do that in a moment. Current will start flowing like that. And now I'm going to break the circuit. So now the current's flowing through a huge magnetic field. You can do other fun things with this. But then you open it up. And that's a self-induction. Collapsing magnetic field induces a voltage much larger than what we were started with. Enough to push current around an arc. It's probably pretty hot. I'm not going to touch it. It could if I get in the way. This is, power companies worry about this. You can YouTube it. They got these big metal conductors and they're switches and they like kind of pull them off. And as they open the switch, you can see these sparks going as they open it up. Sometimes they have to worry about fires. It's the same thing. It's this self-induction. Another term for it is back EMF, if you've heard of it. EMF stands for electromotive force. From what we've been calling it, it means induced voltage. Back in the coil, which sends a current in the other direction to compensate for this abrupt change in magnetic field. That's fun. And Catherine, why is this green?
I was wondering why.
Yeah, it's copper. When you heat up the copper and the way the electrons shift their energy levels, they give off green light. Doo-doo-doo. This is also why you should never just pull your turned on appliance out from the wall. You should always turn it off first, then unplug it. Because if the current's flowing and it's something that has a lot of turns and has a big magnetic field and you just unplug it from the socket, have you ever seen sparks? That's what you're doing. A potential for fire there, not safe. So it's always safer to turn it off first and use the circuitry intended for it rather than just yanking it. I wanted to explain that anyway, but that's what also is happening in those coils. Yeah? Volts.
90 volts of energy to light the lamp. What prevents using a small amount of energy, using the power to collapse a magnetic field to generate more energy?
Oh yeah, this seems like yeah, I'm getting more energy out than I put in, right? Yeah, it seems like this is great. Why don't we use this? Because energy is conserved. Voltage is being changed, but so is the current. Ideally, the power stays the same, and so it's not useful. We're not getting any extra energy. We're not disobeying the second law of thermodynamics. And in reality, we're probably dropping a little power because things aren't ideal and 100% efficient, just like the transformers. Other questions? What can affect the efficiency of a transformer? Various things. The obvious is the coupling. Basically, this guy's got a changing magnetic field and this one needs to feel it. So the more they're aligned so this can feel the change in this guy, the better. So this is lame because they're too far apart. So get them closer. Align them better. What if we could channel these guys' field lines into this guy better? So we put it on an iron core as a closed loop. That helps. So the more this magnetizable this is, the better, ferromagnetic. That helps. The number of turns, so geometry and materials they use are the two biggest factors that I can think of to improve it. Any other questions on the homework? Number one. An iron rod becomes magnetic when? Yes, good. The answer was, let me ask. What's the cause of all magnetism? That's true, more generically. Moving charges. What does a charge have? An electric field. Does it have a magnetic field? Just a charge. What does the charge have to be doing? Moving. If it's moving, then it has a magnetic field also. And so there's two of them on there because electrons are spinning, so the net spins of electron, that's movement. That contributes to magnetism. But it's also going around the nucleus. That's movement. That is a contributor to the magnetism as well. So net spins of electrons and they're revolving, as we discussed, and so does the text. Does that help? Oh, yeah, let me finish reading the question. That's what it prompted me to study for review, but that doesn't actually get to the heart of the question. Sorry. Finish reading. An iron magnet becomes magnetic when? Okay, well now we know what causes the magnetism. The answer was the net spins of its electrons are in the same direction. So just because they're moving around, they have a magnetic field. But remember, one could be moving in one direction and the other moving in the opposite direction. Can you guys do this? Not the same. I practiced as a kid that too. Wait, whoop, there we go. Yeah, so this guy's magnetic field effectively cancels out this guy's magnetic field. So they need to have a net alignment. And so both spin in the same direction, which would be this way, like this. Or like this. So they're like both up or both down. Yes, and the magnetic domains are a cluster of these atoms that align themselves. So inside a magnet, you have all these microscopic atoms and you got those electrons and those individual spins we just talked about, and a group of them can tend to align in one direction. There's a net alignment. Say over here. That's a magnetic domain. But over here they might be going this way. There might be a net alignment like this. You get magnetic domains. And those two, you need a net alignment of those, because if they're all random, they all cancel each other out. You would need most of them to be in one direction.
That's why I thought that one would be the answer.
It wasn't an option. So, magnetic domains wasn't an option. It said its atoms are aligned having plus charges on one side and negative charges on the other. Charges alone, and that's just electric fields, so that had nothing to do with magnetic fields. Positive ions accumulate at one end and negative ions at the other. Again, that's just separation of charges, not magnetic fields. Its electrons stop moving and point in the same direction. Well, we're getting the direction key now, but they're not moving. If they're not moving, they don't create a magnetic field. So the net spins of its electrons are in the same direction. Now we have a moving charge and they're aligned. That was the correct answer. If you have other questions, raise your hand. Move on to some brief review. We've been doing it, but you got the two types of charges. That was important. That they can attract and repel, and you know which attracts which. Likes repel, opposites attract. And that's the same with magnetic poles, norths and souths. And you have the force between them. If you increase the amount of charge or the amount of the magnetic field, the poles, then the force increases. And the distance matters too, right? Remember, it's an inverse square law. If you got two charges and you triple their distance between each other, what happens to the force? 9 times weaker, because it's the 3 squared, 9 times. Right. Inverse square law. And that's the same with magnetic poles. And then we've been talking all over the place about conductors and insulators. Able to move charges or not. Do you remember charging by conduction and induction? Conduction and induction? Which conduction, they have to do what? Be in contact and touch, and charge is free to move. So they need to be conductors for it to be useful. Induction, you get it near, say this is charged, and you bring it near, what happens to the charges here? Good. They get polarized. They rearrange themselves. We're not transferring charge directly over, but you can charge it that way. And then remember, if I touch like this side, then those charges can come off. And then when I remove, it has less of one charge than the other now, and so it's now net charged. That's induction. Through conduction, direct contact, if this was negative, this becomes negative, because they just directly transfer over. Through induction, if this is negative, and I bring it near, and do that touchy thing, this will get charged oppositely and be positive, net positive.
So there's no polarization in conduction? You just don't change it?
Well, they do. You bring it near, and they want to rearrange, but it's conductors, and they tend to move. But as soon as you touch, oh, they just whoosh, come on over, so it doesn't really matter. Electric fields. When I first exposed you to it, electric field is that, effervescent force field around a charge. We've been discussing that. And so if you bring another charge near or into an electric field, it's going to feel a force. It's going to accelerate. Just like you bring a mass into our gravitational field, it's going to feel a force, attracting it down. This charge will feel a force because of that electric field. And again, positives repel positives and attract negatives. What should the test charge, when we say there's a test charge, we want to see which way is the electric field. Which way is the electric field? Towards the negative, away from the positives. And if you forget, we use a test charge. We put a charge in here, and the electric field's going that way, so the charge goes that way. What sign does it have to go that way? Positive. So we use positive test charges to help us remember which way electric fields go. Because if you put a positive charge in there, it's going to go that way. That's the way we define the direction of an electric field. You can put a negative charge in there, it'll go the other way. But you have to know which way the field's going first. We use positives to define the direction of an electric field. Yeah? It's like, say we got two plates. Remember those plates I had for a capacitor? I can hook it up. There'd be an electric field between there. And I could send an electron beam through there, right? Or I can take a water drop. There, that's something we can charge up. The water molecule's polar. It's polarized. One side has more net positive than the other. And you put it in there. That's what it is. We can charge it up. That's what I can get at. Say net overall, this water droplet is positive. Yeah, you drop it in that electric field and it's going to go that way. Anything. Yeah, a proton. If you can take a proton and shoot it in there, that's what will happen.
So we should just think of it as like a hypothetical.
Hypothetical, yeah, that's a perfect word for it. Yes. Real charges will do the same thing. We did that. Electric potential is what? Voltage, good. And they are both defined as? Who said that? Energy per charge. Electric potential, voltage, or energy per charge. So when we say this is 9 volts, that means energy per charge, joules per coulomb. There's 9 joules per 1 coulomb of charge. If you don't have that much charge, it's okay, the ratio is still the same. It's 9 joules per coulomb, energy per charge. So the Van de Graaff generator, remember, had lots of voltage, 400,000 volts. Was it dangerous? No, because there was relatively little current there was a lot of energy per charge, but there weren't that many charges. So overall, there wasn't much energy, and I could touch it and didn't get fried. You rub a balloon on your head, same thing. It can get to a relatively high voltage, but there's not that many charges, so the energy per charge can be high. Just aren't that many charges. It takes work to separate charges. That's how we put the energy in, and batteries do their thing. We started flowing. Remember the difference between series and parallel circuits? What's the same everywhere in a given series circuit? Current, because it has to get through one to the other. It's a complete path, so the current's the same everywhere. What's shared? The voltage gets shared. The energy per charge. This one's going to use up so much, this one's going to use up so much, this one's going to use up so much. And in parallel, it's the reverse. Because the current can split. So it gets shared. Some goes this way and that way. But they all get the same voltage. Because each light bulb could see one side of the battery. That energy per charge. Yeah?
One thing you said that confused me was you said that a fuse or circuit breaker was in series, but if the house is set for a fuse in
little hypothetical drawing here. These are in series with each other. These are in parallel with each other. This is in series with this. Does that make sense? So you can have all kinds of fun circuitry. I kept it simple. If you want to protect your individual device, you want to put the fuse with that device. Say this one. Then you put the fuse right here. I'll just make it a circle. In series with it. Because if you put that fuse here, that's not what I want to do. What do I want to do? I want to put it, oh yeah, here. That's right. If I put it there and it blows, sure, that protects this one, but now I can't use this one because current can't get there. If I wanted to protect the whole circuit, I can put the fuse over here. If it blows though, it protects everything, but I can't use them because current can't get there. So generally the fuse is right there with the device in series with it. But yeah. That's what, yeah. Okay. 10 minutes. Let's end with a few more demos to teach these things. One, because we can review more with this. So who asked about the card reader? Somebody searched something up. I did some reading. Here's what I've come up with. You can think of this as magnetic tape or the strip on your back and it's of your card. And it's got norths and souths and they alternate and change. You can hook them up in all kinds of ways. And every time that it switches from north to south or north to nothing or nothing to south, there's a change in magnetic field. If that moves near a coil, kind of like this, then you induce a voltage in that coil because it feels a change in magnetic field and you can get a little signal out. I'm using a little LED to represent this. And you can read your information. Well, if these get scraped up or scratched or a little demagnetized or smeared, then this, like a scratch, let's take a scratch. That makes an abrupt change. And not only are you reading the bits of information you want, but at one point you're going to get a big spike because there's a quick change there when you hit the scratch. And that gets read also. It might be misinterpreted as a 1 or a 0 and that's wrong and it invalidates your card. So in general what they do, if you by covering it with something, tape, bag, paper, you increase the distance between the read head and the magnets that are changing. And so if I do it up here, are you seeing any change? I can't see it. Somebody tell me. How about now? I'm exaggerating my distance here, but it weakens the signal that's detected. And the signal to noise ratio goes down and it's more likely to read what you want to. And all read heads are different. But basically the paper, increases the distance between the magnets and the reed head to kind of average out those fluctuations you don't want. So it's easier to read. Clever, and thanks. I learned something. This is a bunch of coils of wire, but you see how they're in bunches? Sorry. I meant to do this because watching some of the videos back, I bet the camera couldn't tell this was lighting. Okay, ready? Okay, there. Now maybe you guys could see it better and the camera could see it better. Forgot to turn the lights off. I meant to. Okay. So Nikola Tesla came up with this thing. Each are in little bundles, and there's a phase thing. Basically, the current is alternating current, and it's going to increase in one of these coils, but then decrease, and then increase. That's the change. Get a magnetic field. But each one of these increases and decreases in turn. And so the change in magnetic field, the peak of that change, kind of progresses around. You can do fun things with that. This is a copper disc. The changing magnetic field induces currents in the copper. Well, then they create their own magnetic field, and that magnetic field interacts with the initial magnetic field. Or you can think of it as the coil's magnetic fields are pushing on those moving charges. And they're in phase, so it keeps it turning. So as the disc turns, the magnetic field changes orientation. Well, that's okay. So is this guy, and it keeps it pushing. It's a little generator. And if you go the other direction, it'll go that way. Anyway, it's easier to see with this guy. He's made out of metal. He's a conductor. Is that the right way? No. Play Superman. There we go. Now we're rotating the correct direction. But again, it's through electromagnetic induction. And that's my lead into, you want Nikola Tesla? Well, his ultimate is a Tesla coil. Hello, what this is. So I'll end with it. How many volts come out of the wall? Yeah, around 120. I'm going to put some transformers, these four things in the front, step the voltage, not the power, the voltage up to 8,000 volts. I'm going to ground the thing over here. Then there's a white can back here. You can look at it in a moment. It's a capacitor. Those transformers are connected to the capacitor. It's going to charge it up. Current will flow into there. And it'll store what? Capacitors store charge and energy. Stored in the electric field. So, when it is charged up enough, it's connected to some spark gaps on the back side here. There are little gaps that aren't connected, breaks. If you get enough voltage difference, you can break down air, remember? It'll spark, complete the circuit, and all that energy in the capacitor will dump into this coil. This is a primary that we can see. Here's the secondary. That quick dumping of current into here, it'll feel a change. That'll induce a voltage in this coil, which will cause current to flow in it. And it'll charge into this. And if this charge builds up enough, it'll try to spark through the air. And that's the essence of a Tesla coil. The one circuit's charging and discharging, and then so is this one. There's like two circuits here. And if they're fighting, they don't work too well. You have to have this resonance thing, like pushing somebody in a swing. You want to try to charge this up at the right frequency. That's where it gets difficult to build. But the essence is transformers to step it up, store it in a capacitor, dump it into a primary. Here's another transformer. Build up more charge, get big sparks. Does anybody have a pacemaker? Okay, good. We can do this. All right. We need some drama. Any last minute questions? I'm charged up. We can do this again after exam 4, Friday. Monday and Wednesday after that are for review for the whole semester. So I can pull this back out.